So I'm going to work out the determinant by doing 3 times the determinant of the matrix 3 minus 1k 2 minus 2 times the determinant of the matrix 2 minus 1 1 2 plus 1 times the determinant of the matrix 2 3 1 k. So that is 3 times 2 is 6 minus 1 times k is minus k. Minus 2 times 2 is 4 minus 1 times 1 is minus 1 plus 1 times 2 times k is 2k minus 3 times 1 is 3. So the minus k there is just a plus k, and the double minus there is a plus. So 3 times 6 is 18, plus 3 times k is 3k. Then we've got the minus 2 times 5, so that's minus 10. And then we've got a 1 times 2k and a 1 times minus 3. Collecting those together then, we've got the 18 minus 10 minus 3 is 5. And the 3k plus the 2k is 5k. So that is my determinant in terms of k. We are then told that there are 3 distinct planes as defined by these equations. So the first plane is r dot 3, 2, 1 equals 4, and so on. We need to find the Cartesian equations for the plane pi 1 and pi 2, so the first plane and the second plane. You can see we've already got a Cartesian equation for the third plane, so that's why they're not asking us for that one. So for the first plane, let's replace that r with x, y, z. We can see the normal vector is 3, 2, 1 is equal to 4. Multiplying out, x times 3 is 3x, plus y times 2 is 2y, plus z times 1 is z, is equal to 4. That's my Cartesian equation for the first plane. For the second plane, you can see that I don't have a normal vector. So I first need to work out a normal vector, which is going to be a vector that's perpendicular to this vector, because that vector is in the plane, and also perpendicular to this vector, because that vector is also in the plane. So let's do that. So 1 minus 1 minus 1, dotted with a normal vector that I'm going to call n1, n2, n3, should equal 0. 1 times n1 minus 1 times n2 minus 1 times n3 is equal to 0. So that's me doing the first vector within the plane dotted with the normal vector. I'm now going to do the second vector that's within the plane. So 1, 0, 2 dotted with the normal vector, n1, n2, n3 is equal to 0. Again, multiplying that out, 1 times n1 is n1, plus 0 times n2 is 0, plus 2 times n3 is equal to 0. Right, I am now going to say let n1 equals 1. And let's work out what the other n2 and n3 would have to be. So according to the first equation, we'll have 1 minus n2 minus n3 is equal to 0. Or just 1 is equal to n2 plus n3. According to the second equation, we'll have 1 plus 2n3 is equal to 0. So therefore 2n3 is equal to minus 1, and n3 is equal to minus 1/2. Which I can then plug that in here to find that 1 is equal to n2 minus 1/2. Therefore n2 is 3/2. And I now have my normal vector. So I can replace that normal vector. The n1 we said is 1. The n2 is 3/2. The n3 is minus 1/2. Right, I'm going to just rub some of this working out so I've got some more space now. So if you haven't got all of this copied down, press pause and copy it down. Next thing, I'm going to simplify that normal vector because we've got halves everywhere, so I'm going to times that normal vector by 2 to make the numbers a bit nicer to deal with. So we'll rewrite that as 2, 3, minus 1. So that's my normal vector for the second plane. So I can now write it in its vector form. So we've got r dot the normal vector equals a dot the normal vector. Remember, A is just a general point on the plane, which I've got here as 1, 2, 3. The 1 times the 2 plus the 2 times the 3 plus the 3 times the minus 1 is 5. So therefore, the vector equation of this plane is that. Which means I can get the Cartesian equation of the plane if I do the same thing I did for the first plane and say that it's x, y, z, the general point on the plane, dotted with the normal vector, gives 2x plus 3y minus z equals 5. And that's my Cartesian equation for the second plane. For the third plane, like I say, we didn't have to work it out because we were already told what it was. But I am just going to copy that down underneath. And you'll see why in a moment. Because we are now told that the three planes, A, B and C, form a sheaf, we need to use our answer to part A to explain why K has to be minus 1. So I can rewrite this set of equations of the planes in terms of a matrix. So 3, 2, 1, 2, 3, minus 1, 1, K, 2, multiplied by the vector x, y, z is equal to 4, 5, minus 1. Now, if they form a sheaf, there is not a unique solution to this equation. There's an infinite number of solutions because they are meeting on a line. So if there's not a unique solution to this matrix equation, that means the inverse matrix does not exist. It is singular. Which means its determinant is equal to 0. And remember, in part A, we showed that its determinant was 5 plus 5k, because notice this is exactly the same as what we did in part A. So the determinant 5 plus 5k is equal to 0, therefore k must be minus 1.